Hi, everyone. Welcome to OJAP Talks, the podcast series by IEEE Open Journal of Antennas and Propagation. My name is Masood Ur Rehman. I serve as a lecturer in James Watt School of Engineering at University of Glasgow, and I am the lead guest editor of OJAP's special section on millimeter-wave and terahertz antennas for future wireless networks. Today, it's a great pleasure and honor to host Dr. Stephen Beeby together with his collaborator, Dr. Mahmoud Wagih. Dr. Beeby is a professor at the University of Southampton, School of Electronics and Computer Science, where he leads the Smart Electronic Materials and Systems Group. Dr. Wagih is a research fellow at the University of Southampton. Many thanks to both of you for accepting our invitation.
Thank you very much for the invitation.
So today, together with Dr. Beeby and Dr. Wagih, we will take an in-depth look at the latest advances in wireless power transfer and energy harvesting technologies. Dr. Beeby, your paper in our special section explores the energy harvesting at millimeter wave frequencies. Can you explain the importance of energy harvesting and power transfer at these frequencies, please?
Yeah, certainly. But before we talk about millimeter wave frequencies, if we just talk about the importance of RF harvesting in general, then it enables power transfer when other sources or options for energy harvesting are not available. And this is potentially very attractive powering option for a variety of wavelengths, depending upon the particular circumstances. Now, the benefits for millimeter wave in particular is the opportunity to exploit technologies such as beamforming approaches, which can improve the transfer range. And the increased bandwidth means more opportunity for power transfer to occur alongside communication, which I'm sure Mahmoud would like to talk a bit more about.
Millimeter waves are a great opportunity to make antennas smaller, shrink our systems, and also improve the end-to-end efficiency between the transmitter and the receiver. And for a bit of historical background, millimeter waves first appeared in the space power beaming context. The first paper published in the 1990s aimed at transferring power between different satellites and other objects outside the atmosphere. And the context here is critical because millimeter waves attenuate by both air and water molecules over long distances. So once we get outside of the atmosphere, we can use millimeter waves with a very high end-to-end efficiency. And at the moment, most of the research effort is how we can bring it at shorter ranges in more real-world scenarios within the atmosphere, within the smart cities, and within everyday applications.
So can you highlight the major differences between conventional RF energy harvesting and energy harvesting at millimeter wave frequencies?
Yeah, and the main difference, or one of the key differences, is the RF materials. And these materials at millimeter wavelength, and in particular their current high cost is an obstacle to practical deployment. Again, I think Mahmoud has some further comments on this.
I think power transmission and harvesting at millimeter waves are a big opportunity, but also could have considerable challenges. The great thing about antennas and passive electromagnetic components is that they are linear systems. They're very scalable. If you take a 1 gigahertz antenna, scale it down 100 times, it operates at 100 gigahertz. Similarly, if you take the same area and increase the frequency by 100 times, you get 100 times higher gain at both your transmitter and your receiver, and you end up with 100 times better power transfer efficiency. This is only true if materials hold their properties, and unfortunately, they don't. Similarly, there are challenges in the semiconductor devices and the electronic systems that integrate with millimeter wave power transmission using antennas. Our closely related community, microwave engineering, actively looks at how we can make semiconductors, whether that's new materials or leveraging digital CMOS to generate more output power, higher power for millimeter wave frequencies in order to support longer range power transmission and communication efficiently.
Okay, so what are the key performance indicators you are using for a wireless energy harvesting and power transfer system?
Well, if we think about energy harvesting in general first, our primary objective is to deliver sufficient energy for the application. Factors such as efficiency become important when other application constraints become a factor. So, for example, achieving a sufficiently efficient operation to deliver the required energy and meet size, volume, and form factor constraints. As with other types of energy harvesting, the use of the technology is dependent upon the application, and the relative importance of the performance indicators is also similarly application dependent. Another key consideration is the nature of the electrical signal after it has been converted from the energy source. So achieving, for example, a sufficiently high voltage can affect the efficiency of other parts of the energy management process, such as rectifying the signal. So systems should be designed holistically to maximize the overall system efficiency rather than just concentrating the efficiency of one particular component.
Right. As I understand, rectifier circuits play a very important role in energy harvesting and power transfer systems. What are the key challenges a designer has to take up to achieve an efficient energy harvesting system?
So the choice of diodes, so matching the diode characteristics to power levels, for example, finding suitable diodes, especially at higher frequencies, can be very challenging. Mahmood?
As Steve highlights, it's all about the challenge and it's all about the application. At millimeter waves, we need to know our challenge. We need to know how much power we're expecting to receive and how to overcome the losses of commercially available components. At millimeter wave frequencies, we are beyond the cutoff frequency of conventional silicon Schottky diodes. We start to look at more exotic, lower yield semiconductors like gallium arsenide, which are high cost components. We can't avoid them, except if we start to integrate our systems in digital integrated circuits in the ever so small scaling digital CMOS processes. So advice to the designer is to keep your options open. For example, a rectifier in a digital CMOS process in a deep submicron process can outperform its counterparts based on off-the-shelf diodes while maintaining a significantly lower cost than a gallium arsenide diode dedicated for much higher frequency and much higher power applications. And don't just think about the instantaneous power conversion from RF to DC. Consider what you do with the energy rather than that power. Can it be stored efficiently in a supercapacitor? Can it be boosted efficiently with the DC to DC converter? And if not, then why? And more importantly, what can you do as an RF antenna designer or a matching network designer to get more useful, and I stress useful, DC energy through improving the RF incident voltage you collect from your free space radiation?
Right. Antenna is the backbone of any wireless system. So how does the antenna design affect the energy harvesting and power transfer at millimeter wave frequencies?
So yeah, absolutely. Antenna design is key, and it's important to appreciate that it's influenced heavily by the application and the use case scenario. So obviously, it's important to understand the environment the antenna will be operating in and how this might change in mobile / wearable applications. Mahmood?
Yeah, we've looked into antenna requirements, and in our review paper published in the IEEE Antennas and Propagation magazine, we've shown that you can't just take a single antenna metric, say for example the gain, and take that as the sole figure of merit for a power transfer or energy harvesting system. In a rectangle, there are more parameters. For example, polarization is a critical factor, and in a mobile system, polarizations need to match, or our system needs to have the dynamic range and the ability to harvest different polarizations. Similarly, the beam widths of the antenna, and that's more critical at millimeter waves, where we start to see technology as beamforming networks and multi-beam antennas. That beam width needs to cover the angles where you expect the power to come. And in a mobile system, that becomes a bigger challenge because we need both high gain to overcome the path losses at millimeter wave frequencies, but we also need wide angular coverage. When we also think of antennas when they integrate with the rest of the system, we always design antennas with a 50 ohm characteristic impedance. And that's a trade-off that comes from coaxial cables. We don't see coaxial cables in antennas, which are normally large area components. And that's why we need to rethink our design strategy and standards. Antennas can overcome the losses in a matching network. They can double as a voltage booster by designing them as a high impedance antenna to increase the wave that the rectifier sees and reduce the losses within the semiconducting junction of diode, and that will enable us to harvest power at longer ranges, while reducing the complexity of the circuit, all through antenna design based on new requirements that come from the energy harvesting application.
You're also doing pioneering work on flexible electronics, smart materials, and fabric antennas. How energy harvesting and wireless power transfer can play a part in these areas?
So the main focus of my work is in electronic textiles, where I'm aiming to make fabrics a platform for wearable technology and wearable systems. So one key challenge is that no matter how well we integrate the sensing and electronic functionality within the textile, we are currently still relying on conventional rigid batteries that are incompatible with the feel of a fabric, and the need to remove these prior to, for example, washing should be avoided. So my group is looking at a variety of energy harvesting approaches for flexible and e-textile systems, along with flexible energy storage devices, such as textile supercapacitors and batteries. The RF power transfer / energy harvesting is an important component of these activities and presents many advantages, particularly in well-confined, well-constrained environments, such as, for example, recharging devices when they're placed in a wardrobe. Wireless power transfer can also achieve higher efficiencies than other energy harvesting sources. The implementation of RF systems in e-textiles presents some challenges, but is entirely possible using textile-compatible fabrication methods, and Mahmoud will explain this further.
So integrating antennas and RF hardware more generally with e-textiles and flexible large area electronics is both an opportunity and a challenge. But low-cost printed materials or textile-based materials are not a hindrance to good RF performance. We've shown that we can print passive components and antennas up to millimeter wave bands on textile materials with very high efficiencies and low insertion losses. And we've also looked at how we can adapt different transmission lines and waveguiding mechanisms using new techniques such as surface waves to carry signals efficiently at millimeter wave bands around the human body, overcoming both absorption by the human tissue and losses in the materials, which are not usually as good as solid copper or conventional RF laminates. Wearable antennas are also very promising. E-textiles are the closest non-invasive interface near the human body. Flexible and textile antennas can be many times more efficient than integrated antennas in our wearable devices as we know them, for example, smart watches, and that's because of the large area available to the user. So it's up to us antenna designers to leverage this large area opportunity, which comes with some material-based challenges, in order to improve the connectivity of user-centric devices and of electronic devices operating very close to the user.
Right. So in your expert opinion, what are the prospects of energy harvesting and power transfer in future wireless communication systems such as 6G?
Well, it will be use case dependent, but the technology is clearly progressing in such a way that the RF power transfer will become an attractive and cost-effective approach for powering and recharging systems in well-defined application scenarios. So Mahmoud's work on simultaneously supplying power and communicating has illustrated the feasibility of this approach, and I'm sure he'll describe this in more detail.
I think from a power transfer point of view and how it could be integrated in wireless communication, coexistence is key. And antenna engineering matters for these applications to be realized. The practical question will be who is transmitting the RF power, how much power is being transmitted, at what time, and in which bands. And that's where millimeter waves come in handy, because we have enough channels to coexist alongside cellular communications. Also, how to transmit information and power together, and what antenna solutions are needed to enable simultaneous wireless information and power transfer, or SWIFT, as a physical reality, is an important research challenge. SWIFT as a concept has been extensively studied by the wireless communication community, but only until very recently, there has been very limited implementations from an antenna point of view that address SWIFT. In our most recent OJAP paper, we have looked into how we can leverage SWIFT by designing antennas to support both information and power transfer in license-free bands, while also satisfying the requirements of more complex communication systems like multi and multi-add MIMO systems, and also full duplex systems, which enables us to extend the capabilities of both communication and energy harvesting in wearable systems. This goes to show that power transfer can coexist and that the solution to a problem like power splitting or scheduling the power delivery and the information delivery can be solved through innovative antenna design and not just through signal processing.
Very interesting. Dr. Beeby, you have a very unique career path with over 140 journal papers, 190 refereed conference papers, 4 patents, and 27 invited talks. What experience you would like to share with our readers and young professionals to become a successful researcher?
Well, this is a great question. That it made me sort of look back and think about my career path, which was nice to do. So the first thing I would say is be strategic. Think about where you want to be and have a clear vision for your career goals and understand the rules of the game. So what do you need to do to get there? Be focused on what you do. So work efficiently towards the goals. Try not to get distracted unless that's actually constructively helping you in another way. Working in academia as a young researcher is you're obviously expected to publish papers, but don't neglect other factors such as building esteem, communicating with the public, networking, and engaging with industry where possible. Seek opportunities to demonstrate leadership and independence. And a word here for senior academics, people who are supervising or mentoring junior staff, for example, try to provide opportunities for young researchers and encourage encourage that they take on leadership roles, for example. Gain experience in preparing funding bids as early as on. So maybe work with your supervisor to prepare funding bids and working yourself into a position where you're able to apply for a fellowship, for example, will certainly accelerate your development. Where possible, work collaboratively so you can achieve much more if you work effectively in small teams. So again, if you're working alongside colleagues, try to have small projects that you can work together on, and you'll be surprised what you can achieve. Keep up with the literature. So this may sound obvious, but it's really important to take time to review papers, understand the latest developments, who's doing what, etc. And be flexible in your work. So don't get stuck in your ways, and be prepared to learn to appreciate other technologies that ultimately will influence the areas of your research and where you're working. I hope that's helpful.
Very interesting. Thank you, Dr. Beeby and Dr. Wagih, for joining me at the OJAP Talks. It was a pleasure talking to you, and you have enlightened us with this great, insightful discussion. Thank you very much.
Thank you. It's a pleasure.
Thank you.